Hey, what's going on, folks? It's Mike here, and welcome to another lesson in the C++ series. In this lesson, I'm going to be talking about and introducing the first of three types of smart pointers available in modern C++. So let's go ahead and do a little refresher and then learn about a new type of smart pointer called unique pointer. So where I want to start in this lesson is just reviewing a little bit. Maybe you're just hopping to the series now, or maybe you've watched everything prior to this video and you have a good understanding of things, but let's just put everybody on the same page for a moment. So for this example, what I've done is created an integer here, and then I have a pointer that stores the address of x. And then if I dereference our pointer here and print out the value here, well, our pointer points to x, and when I dereference it, we should get 42. And then maybe later on in my program somewhere I decide, hey, I'm going to do something interesting here and create another pointer, and it's going to point to, well, whatever this pointer it's been assigned to, and copy the address of what is stored there. So in effect, we are sharing here, and that's one of the major ideas of pointers. So then we want to go ahead and continue on in our program and dereference pointer 2 here and just print out the value. So I'm going to go ahead and compile this here. And if I run this program, you'll go ahead and see, as you would expect, pointer, the first one, and pointer 2, well, since they both store the same value of x, 42 is printed out here. So raw pointers allow sharing. And that's something that we've talked about, or I've talked about in various lessons prior to this, but that's one of the powers of pointer and why we often like to use them. We can use this powerful idea to build and aggregate data structures or otherwise update multiple pieces of data at once, which is pretty cool, as you can see in this example. But what this example is lacking is some sense of ownership. And not to mention, there are dangers with pointers if we forget to delete stuff or once we start allocating things on the heap. So let me go ahead and demonstrate. So I'm going to go ahead and change this example slightly here. So what I'm going to do instead is make x heap allocated. And let's go ahead and make a new integer. In fact, let's make 100 new integers here. And I'll still create my pointer, and maybe we'll do a little bit of work here to just initialize our values. So I have a for loop, I less than 100, I plus plus, x. And let's give this a little bit of a better name here for some array that's been allocated on the heap, and just assign some values as such here. And I'll make this a little bit smaller so you can see everything. And we'll create our pointer, which now points to the start of the array. And let's go ahead and run this program here, make sure that it compiles. And oops, we don't need the address because, well, we just point directly to the array. And I can run this program and, well, the first value that's pointed to is 0. But what have I forgotten to do here in this program with this heap allocated array? Well, the first thing is that I've forgotten to do is to delete. Okay, so let's go ahead and try that here. So what I'll go ahead and do is make sure that I call delete here. And I want to delete my array here. Okay, so let's go ahead and run this program. And, well, it runs, it still does something interesting, but the astute reader and someone who's watched and subscribed and seen the other lessons has noticed that, well, I've made another mistake here. If I actually run this program through a memory checker, whether that's one of the sanitizers in the compiler or a tool like Valgrind if you're on Linux, you're going to notice that we have leaked some memory here. So let me go ahead and compile this with debugging symbols. And I'll go ahead and do -g here. And oops. Make sure that I run with the standard C++20, although we don't need that for this particular example here. And let me go ahead and rerun our program here. And again, we have to be a little bit careful here, and I'll move out of the way. But it's saying, hey, all the heap blocks were freed. But if I actually scroll up through this output, you'll notice that it says there's a mismatch free and delete with the brackets. So again, this is one of the things that makes things really fun in C++, where we have to make sure that we delete the array with the brackets here. Okay, So that is the other mistake. I'll recompile this. I'll rerun it here just so that we can see it runs. And now if I run this with a tool like Valgrind, we'll see that it is completely happy here. And it might have even been giving us a little bit of a false positive if you were to just read the bottom here that said all the heap blocks were free. Now, regardless of how you look at this program here, raw pointers, while they allow sharing, I'm going to argue they allow room for errors. Meaning, forgetting to deallocate. And in addition, the other problem or thing that we have to at least think about with raw pointers, not that it's a problem, it's just something else that we have to think about and manage, and in a big software project that can often be a problem, is ownership. So that is to say, in this particular program, what if I had said, well, I'm going to delete the array before I assign this pointer to the other pointer, and well, what does it point to? So let's go ahead and recompile this. And if I rerun it, let's go ahead and see what happens. You know, it might happen to work, but I've deleted some memory. So if I do something else here on the heap, like allocate a new array. So later in my program, I just allocate a new, and let's make it a new float array or something like this with 100 elements. And let's just see if we can get this program to do stuff a little bit wonky here. It's happened to be zeroed out here because our memory is 0. So let me go ahead and just make this I+1 or something like that. And I'll rerun this. And well, again, we're getting lucky that we don't have any sort of heap corruption here. But if I've deleted the array that I'm pointing to by both pointer 2 and pointer 1, you can see clearly that, you know, our program is not working. And depending on the system you're on, I'm on Linux, the C runtime or C++ runtime might be smart enough to not crash and just give you a 0. And on your other systems, you might actually get a crash here. So again, there's these sort of problems here. You know, was it appropriate for me to just delete this array here? So with all this said, with all this introduction, and hopefully you have an idea of what's going on in the pointers, I want to introduce what's called a smart pointer, which fixes some of these problems here. So smart pointers address these issues. Okay, and that's broadly speaking about ownership, who owns the pointer, and helping make sure that you can deallocate or don't have to worry about when you deallocate your memory. So let's go ahead and look at one, and hopefully this will make a little bit more sense here. So I'm going to clear our little exercise here talking about the problem of pointers and introduce some new things here. So what I'm going to introduce is a new library here called memory, and that's where our first smart pointer exists, called unique pointer. And what I've done to just set up this example to make it a little bit more compelling is create a user-defined type. Now in this series, I haven't talked about classes, but I'm assuming you'll be able to understand this, where I'm basically creating my own data type here. As soon as I create that data type, the constructor is called, so I'm just going to print that off. And I have a destructor, that's with the little tilde mark here, that's going to call the destructor immediately. So let me go ahead and just run this, where if I wanted to create my user-defined type and give it a name, something like this. And if I run the program, you'll see that the constructor, that is this member function here, is automatically called, and the destructor here is automatically called when we leave scope here. That is the brackets. And this idea of, well, leaving scope and having something automatically happen is really important in C++. In fact, I'm going to have a dedicated lesson to it on this idea of RAII. So I'm going to highlight that here, RAII, and that basically just means scoped is when we're going to create something or destroy something. And that's what our smart pointer is going to be that we're going to look at today, which is the unique pointer. Okay, so let's go ahead and just take a look at and see how this actually works. So what I'm going to go ahead and do is make a smart pointer here called a unique pointer, and it's a templated type here. So let's go ahead and just use this user-defined type here. I'll just call it my name here, and let's just start with that here. So I can go ahead and compile this, run it, and well, nothing happens because it is a pointer and I haven't allocated any memory. So how do we allocate memory? Well, we do so in a similar way where I do an assignment here, and this is for a unique pointer. I have to provide the type here and then any arguments for the constructor here. So let's go ahead and see if this works. Now, we're going to have to do one additional thing here. So let's go ahead and see if our compiler yells at us here. It is going to complain here because, well, it's not enough to just say this is going to be a new pointer, but we have to allocate some memory. So I have to say I want a new user-defined type here in the parentheses. Okay. Oh, and let me make this a little bit bigger here so you can see the error message that's occurring. And I've just accidentally typed in Mike here. So I'll go ahead and put in the right template argument that matches here. Okay, so with that said, let's go ahead and recompile. And now we see things are working. So now if I go ahead and run my program, you'll see that this type is created and destroyed because we've actually created this UDD type. And it is in fact something that exists on the heap because we have allocated with new here. So we've allocated it and I don't have to worry about calling delete, for example, Mike here. Okay, let's go ahead and see what happens if I try, just if you're curious. And in fact, it's going to say, hey, you're not supposed to do this. You can't delete a unique pointer because it is a scoped pointer. It's going to delete itself once it leaves this brackets. And let me be a little bit more precise here. I mean the curly braces here. So we don't have to call it delete. That is one of the first major advantages. It's going to take care of deleting itself, and we don't have to worry about, you know, am I supposed to call, for instance, delete, or is it delete with the brackets here? Don't have to worry about that. So even if I initialize this as an array, so let me go ahead and show you some examples, creating one unique pointer. And let's go ahead and create an array of unique, or I should just say an array that is pointed to by one unique pointer. Okay, so how do we do that? Well, it's going to look similar. I'm just going to copy this line here. And if I want to just create a raw array, let's go ahead and add in the brackets here. And then we want to say, well, how many of these new things are we creating? Let's say 100. So let me go ahead and compile here. Let me go ahead and give this a new name, Mike array, just so you can see the two different ways to do this. And if I rerun our program, well, all of a sudden, since I've created 100 of these, we're going to get the destructor called many, many times here, as well as you can see all the different times that when I created this type that it was created. So that's pretty cool that you can do this. Now, this particular syntax that I used here, and let's go ahead and 100's a little bit overwhelming, so maybe just 10 is reasonable here, is not the preferred syntax here. So instead, what folks will do, instead of having to remember this, and there's all the sort of templates, is they'll use another function here, which let me go ahead and just show you the equivalent. So the equivalent to the line above is, and I'll go ahead and do this with our Mike array, is to use a function called make unique here. So that's going to be make unique. And I need to make sure I spell it right here. And what make unique is going to do is, well, instantiate or create however many of the items that we want. So we want this UDT, this user defined type. It is still an array. And how many of them do I want? Well, let's just work with 10 again so that we can see the example run and do the same thing. Okay, so here it is. And this is the preferred syntax. For those who are familiar with various design patterns, this is what's known as sort of a factory pattern, where it is making this type for us. And again, it's just doing the right thing. It knows which constructor to call and so on. All right. So now that we've looked at this a little bit, let me go ahead and revisit our whiteboard for just a second here. And let's go ahead and summarize unique pointer. And I want to show you a few more use cases of why this is powerful and why we should be able to use this. So with unique pointer, and I'll write it out as the type is, we cannot share, which I'll demonstrate. That is, no copies are allowed. We don't have to delete. It deletes within the scope. Okay, and that means the block scope. So within the curly braces. And again, that can really simplify our job or our lives of having to manage code. So let me go ahead and show a few more use cases with unique pointer here, just so you can see again what it protects us from. So let me go ahead and make our code window a little bit larger here. And let's go ahead and just work with one of these arrays. I'm going to just comment this out so it's on the screen, so it'll always be available for you. But let's say that I do go ahead and create another pointer here, and I'll just give a different name here, Joe or something. And I decide that I should just point Joe to Mike here. Okay, so this is what I'm going to try to do here. So I'm going to try to create this new pointer and or make a copy of it by calling the copy constructor. And immediately you're going to notice that I get a bunch of errors on the right side, and this time I am intending to actually make those errors because it's saying, well, you're just not allowed to make a copy here. In fact, if I open up the C++ reference page, our favorite page to look at, so let me go ahead and bring that in here. And let's just go ahead and search for unique pointer. And I'll go ahead and search for this, grab it here. And if we look through the actual page here, if I look at the actual operators here, I don't see a copy constructor. In fact, let's go ahead and just search for copy. In fact, it says this class is not copy constructible if we actually search for it, when we search for it. So we're not going to find any sort of copy constructor here if you look through the reference or the actual standard library C++ code. You'll find that it is deleted. So again, this itself is not allowed here. Okay, now we are allowed, however, to transfer ownership. So we can move Mike into Joe here. So if I run this code, this is allowed. So just to be for folks who have watched the move semantics and the L value and R value videos previously in the series, we are allowed to move. So we are allowed to move a unique pointer, which essentially transfers the ownership of whatever was in Mike to Joe, and now Mike is nulled out or whatever. But we cannot copy. But we cannot copy with unique pointer. And folks usually want to see a visual of this, so let me go ahead and just kind of draw what this means here. So again, if I have Mike here, and I was pointing to some memory here, my user-defined type, when I create Joe here, who is the other pointer, and when I do the move, as soon as I do the standard move, I own this memory. But again, with unique pointers, we can't have two things pointing to the same box of memory. So that's where the ownership comes in. And in a sense, we're disallowing sharing. So this allows us to point to things or heap allocate, say, really big blocks of memory. And again, just so you can see the diagram here, but we cannot share. So I cannot have two arrows coming into this same block of memory with a unique pointer as the name implies. All right, so that's the idea with unique pointer. So we cannot share. No copies are allowed. We don't have to worry about deleting the right thing or not. We do have move semantics. So move is allowed. And overall, it can simplify the memory management in our actual code. So folks, I hope you enjoyed that lesson. I hope that was a nice introduction to smart pointers, showcasing some of the problems with raw pointers that can happen if you were unfamiliar with that. And now you have a new tool in your arsenal if you include the memory library. So if you want to go ahead and see the next lessons where I'm going to talk about the other types of smart pointers, make sure you subscribe and make sure you comment below if there was something confusing or that you didn't understand. I've tried to show a bunch of the syntax, which takes a little bit of time to get used to, but go ahead and practice and I'm sure you'll get it. All right, take care, folks.